Hi everybody, the purpose of this video is to go over section 6 of chapter 8, and in this section we are going to use de Moivre's theorem to compute the powers and roots of complex numbers, and this theorem makes life a lot easier for us. Okay, so let's start off with this particular problem. We want to find we want to raise the root 2 plus I times root 2 to the 5th power. Okay, and we want to write that answer in rectangular form. So how can we do that? Well, we go ahead and square it, and if we do, we will get 4i, and then we can take 4i, we can multiply that by root 2 plus I times root 2 to get the cube value, and we will get this, which is negative 4 times root 2 plus I times 4 times root 2. We can then take this and multiply this by, we can multiply that product by, or this sum by the quantity root 2 plus I root 2, and that will give us the 4th power, which is conveniently negative 16. And then we can take negative 16 and multiply it one more time by root 2 plus I times root 2 to get the 5th power, which of course will be negative 16 times the square root of 2 minus I times 16 times the square root of 2. It turns out there happens to be a slightly easier way to do this. And one way might be is to use Euler's formula, which we talked about at the very end of the last section. And remember, root 2 plus I times root 2 is the rectangular form of complex numbers. The polar form of this would be 2 times CIS with the angle of pi over 4. And of course we could actually get that because the square root of the sum of the square of the real and the imaginary parts is going to be 2. And it turns out that theta would be equal to 45. And then again, we could also write this in exponential form as this using Euler's formula. Okay, let's take a look at that. And that's the case, then raising this to the 5th power is the same thing as raising this to the 5th power. And this we know how to do using our property of exponents. We can actually apply the power property, and this would be equal to 2 to the 5th and times e raised to the I pi over 4 power, that to the 5th. Okay, we know how to do that. And of course this is 32, and then here the exponents multiply. We will have e raised to the I 5 pi divided by 4 power. And of course then we can convert this back into trig form, which would be 32 times the cosine of 5 pi over 4 plus I times the sine of 5 pi over 4. And we know what those are. This is negative root 2 over 2. And this is also negative root 2 over 2 because we are in quadrant 3. And we would get the exact same answer, just a lot simpler. And right here is an application of de Moivre's theorem. And this is what it says. If r times cosine theta plus I sine theta is a complex number and n is any real number, then the following holds true. This number raised to the nth power is going to be nothing more than r raised to the nth power times cosine of n theta plus I times sine of n theta. In a compact form, it would look like this. And actually, this is very, very easy to prove. And we're going to prove this using a complex exponentials. And of course, we've pretty much already did it. This, as a complex exponential, can be written as r times e to the I theta. If I raise that to the nth power, I am going to have r to the nth power times e to the I n theta. Writing this in trig form, you have r to the nth power times cosine n theta plus I sine n theta. So with the use of complex exponentials, this is very, very easy to prove. And of course, that brings us to example time. Suppose we want to find the fifth, or we want to raise square root of 3 plus I to the fifth power, and we want to write our answer in rectangular form. Well, the first thing we want to do is we want to convert this into trig form or polar form. And we can do that by finding r. R is going to be equal to the square root of the square of the real part, which is 3, plus the square of the imaginary part, which will be 1. And of course, that's going to be the square root of 4 or 2. Now, theta is going to be in quadrant 1, because we basically have positive real part, positive imaginary part. That's quadrant 1. And that means that theta will actually be equal to the arctangent of the imaginary part, which is 1 divided by the real part, which is the square root of 3. And that will give us 30 degrees. Okay, so that means that root 3 plus I can be rewritten in polar form as 2 times cosine 30 degrees plus I sine 30 degrees. Okay, and then by de Moivre's theorem, we will have that root 3 plus I raised to the fifth power is going to be equal to 2 to the fifth power, which is 32, times cosine of 5 times 30 degrees plus I sine of 5 times 30 degrees. That will be 32 times the cosine of 150 degrees plus I sine 150 degrees. Now, to convert this into regular form, we just need to compute the cosine and sine of 150. Notice that these have reference angles of 30 degrees, but we're in quadrant 2, which means that cosine will be negative. So we are going to have 32 times negative root 3 over 2 plus I, and then sine of 150 is going to be positive in quadrant 2, but it's going to have the same value as the sine of 30, which is 1/2. And then our final answer will be negative 16 root 3 plus 16I. And there you go. Now we need to talk about the nth root of a complex number. So let's call that's that n being any positive integer. Here it is. Then we are going to say that the complex number a plus bi is an nth root of this complex number if we raise a plus bi to the nth power and get the original x plus yi. And this works best when we are dealing with complex numbers in trig form. Okay, and let's just take a look at an example. So let's let x plus yi be equal to 64 times the cosine of 60 plus I times the sine of 60. We want to find all the cubed roots of this particular number, and there will be 3 of them actually, and there will be 3 of them. Okay, so we want to find the numbers of the form r times cosine alpha plus I sine alpha, such that when you cube this, you are going to get 64 times the quantity cosine 60 plus I sine 60. Well, if that's the case, we can apply the Moivre's theorem here, and we can rewrite this as r cubed times the cosine of 3 alpha plus I times the sine of 3 alpha is equal to 64 plus cosine of 60, or times cosine of 60 plus I sine of 60. And notice that these will be true if r cubed is equal to 64, and when cosine 3 alpha is equal to cosine of 60, and sine of 3 alpha is equal to sine of 60. Well, that basically will only occur when these two equations can only be satisfied when 3 alpha is equal to 60 degrees or any angle that is coterminal with 60 degrees, which is why we have the k here. So if that's the case, solving for alpha, alpha has to satisfy this equation for integer values of k. So let's take a look at certain integer values of k and see what we get. First one will be the trivial one. It's just k be equal to 0. Then alpha is 20. Okay, so that's going to be one of the solutions. What about when k is equal to 1? Well, then that's going to be 60 plus 360, which is 420, divided by 3 is 140. What about when k is equal to 2? Well, that's going to be 60 plus 360 times 2, which is 720. That's 780 over 3, which is going to give us 260. What about when k is equal to 3? Well, that is going to be 60 plus 360 times 3, which I believe is 1080. Yeah, 1080, divided by 3, which is 380 degrees, which, by the way, is coterminal with that. So we don't really need to use this because that is going to produce an angle which has the exact same sine and cosine values. And if we went to 4, that angle would be coterminal with 140, and then at 5, this would be coterminal with 260, and we would just keep going around. So once we get to k is equal to 2 or k is equal to 3 minus 1, we found all the angles that we need to find. Okay, and if that's the case, then the cubed roots of 64 times the quantity cosine 60 plus I times sine 60 are the complex number 4 with an angle of 20, the complex number 4 with the angle of 140, and the complex number 4 with the angle of 260, and you can see these complex numbers right here. And that basically is an illustration of the nth root theorem, which basically says this: if n is any positive integer, and if r is a positive real number, and theta is in degrees, then the non-zero complex number r cosine theta plus I sine theta has exactly n roots. And the roots are given by this equation, or that equation, where alpha is determined by this, and is the 3 different values of alpha, or the n different values of alpha that give you your n roots. If it's in radians, we just replace 360 with 2 pi, and we do the exact same thing. Okay, so let's actually work this out in an example. So we want to find the 3 cubed roots of -8. Before we can do this, we need to write this in polar form. Okay, so how do you write -8 in polar form? Well, that will be 8 times the cosine of 180. Cosine of 180 happens to be -1. Plus I times the sine of 180. Which happens to be 0, so it actually does indeed work out. If that's the case, and once we have that, we can apply our nth root theorem to find the 3 roots. The first root is going to be, well, first the cubed root of 8, which is 2, times the cosine of 180 divided by 3 plus I times the sine of 180 divided by 3. That is going to give us 2 times the cosine of 60 plus I times the sine of 60. Let me close the parentheses here. Okay, and we can convert this into rectangular form. That is going, the cosine of 60 is 1/2, so that's going to be 2 times 1/2. And then the sine of 60 is the square root of 3 over 2 plus I times the square root of 3 over 2. And then we will have our final result for this one, which will be 1 plus I times the square root of 3. Okay, now for the next one, root number 2, that is going to be 2 times the cosine of 180 plus 360 over 3 plus I times the sine of 180 plus 360 over 3. That is going to be equal to, conveniently, 2 times the cosine of 180 plus I times the sine of 180. And we can all recognize that as negative 2. Cosine of 180 is negative 1, sine of 180 is 0, we have negative 2. And then finally, we are going to have 2 times the cosine of 180 plus 720 over 3 plus I times the sine of 180 plus 720 over 3 and that will be equal to 2 times the cosine of 300 plus I times the sine of 300. That is an angle in quadrant 4 with a reference angle of 60 degrees. And if that's the case, then we will have 2. The cosine of 300 is going to be like the cosine of 60, which in quadrant 4 will be positive, so that will be 1/2. And then since we're in quadrant 4, the sine of 300 will be the sine of 60, but it'll be negative, so that'll be minus I times the square root of 3 over 2. And then that will be equal to 1 minus I times the square root of 3. And there we go. Those are our 3 roots. Okay, one more example. Let's find all the 4th roots of this sucker. Okay, once again, we need to figure out what R is. R is going to be equal to the square root of 128 squared plus 128 squared times the square root of 3 squared, which is just going to be times 3. That's going to be equal to the square root of 4 times 128 squared. And that will be equal to 2 times 128, which is equal to 256. Okay, now theta is in quadrant 3. No, not equal to quadrant 3, but it's in quadrant 3. So that means that theta is going to be equal to the arctangent of the imaginary part over the real part, which is going to be the square root of 3, plus 180 degrees. That's going to move us over from quadrant 1 to quadrant 3. And that will give us a tangent value of 240 degrees. 60 plus 180. And theta will be equal to 240 degrees. So that means that negative 128 minus 128 I times the square root of 3 is going to be equal to 256 times the cosine of 240 plus I times the sine of 240. Okay, so now we can go ahead and find our 4th roots. The first one is going to be, well, first thing is the 4th root of the 4th root of 256 is equal to 4. So the first root is going to be 4 times the cosine of 240 divided by 4 plus I times the sine of 240 divided by 4. That is going to be equal to 4 times the cosine of 60 plus I times the sine of 60. And that will be equal to two plus 2I times the square root of 3. That should be an I. There we go. Okay. Now the next one is the next root is going to be 4 times the cosine of 240 plus 360 divided by 4 plus I times the sine of 240 plus 360 divided by 4, and that will be equal to 4 times the, forgot to close the bracket there, 4 times the cosine of 150 plus I sine of 150, and that will be equal to, well, the cosine of 150 is going to be negative root 3 over 2, so this is going to be negative 2 times the square root of 3 plus 2I. Okay, and then for the third root, we will have 4 times the cosine of 240 plus 720 over 4 plus I times the sine of 240 plus 720 divided by 4. That is going to be equal to 4 times the cosine of 240 degrees plus I times the sine of 240 degrees, and that will be negative 2 minus 2I times the square root of 3. And then finally, for the last root, you will have 4 times the cosine of 240 plus 1080 divided by 4 plus I times the sine of 240 plus 1080 divided by 4, and then that will be equal to 4 times the cosine of 330 degrees plus I times the sine of 330 degrees and then that will give us two times the square root of 3 minus 2I. And those will be our 4 roots, which are sort of right there. Okay, the last example has to do with solving an equation. And here we want to find all the complex roots, or all the complex valued solutions of 6x cubed, x to the 6th power plus I is equal to 0. Of course, that will occur when x to the 6th power is equal to negative I, or when x to the 6th power is equal to 1 times the cosine of 270 plus I times the sine of 270. That will give us a negative 1. As you can see, the solution to this particular equation is going to be the 6th root of this particular number, and there will be 6 solutions. So how do we figure them out? Well, here we only need to figure them out in polar form, so we can just go ahead and write them out. First, let's go ahead and write this in the abbreviated form. This will be CIS 270. And then the 6 solutions will be this. First one will be x1, which will be CIS 270 divided by 6, 270 divided by 6, which will be CIS 45 degrees. The next one is going to be CIS with an angle of 270 plus 360 divided by 6, and that will give us a CIS of 105. The third one, that will be CIS of 270 plus 360 times 2 over 6, and that will give us an angle of 165 degrees. And then, and you'll notice that basically all the numbers are the same. It's just that basically the angle increments by 60 degrees. So x4 will be CIS of 270 plus 360 times 3 over 6, and that will give us a CIS of 225. X5, hopefully that will give us a CIS of 285, which of course it will. 285, and then finally for X6, that is going to be CIS or complex or compact form of 270 plus 360 times 5, all that divided by 6, and you guessed it, that is going to give us a CIS of 345. And this right here is a graph of the vectors in the complex plane, courtesy of GeoGebra. And that is all I have for this particular video. If you have any questions, please feel free to contact me. This is Bob Boyle signing off.